pleasure to have here with us Rafael Sánchez, to whom I think most of you know. He was here for many years in our lab. He did a PhD here in our group many years ago, and then he went for a postdoc with Marcus Butiker, and then afterwards he got the Ramón y Cajal position, and then went to the university, the Autonomous University, and now he has a permanent position there at the IFIMAC, at the Condensed Matter Theory Department. Mm-hmm. And Rafa is an expert in quantum transport and also in quantum thermodynamics, and he's doing a very much active research, and today he's going to speak about single-electron or photon heat currents.
Okay, thank you, Gloria, for the introduction. It's a pleasure for me also to come back to the Institute after some years without being too much here. We seem to be not so far from each other, but in fact there is a huge separation with this parking that, I don't know, avoids people to go from one place to the other. Apparently, I don't know. We have many examples of this. No? So okay, what I will talk about today is about how to control heat. This is something that in a few months will be a big problem for all of us in the summer. No? So, and we know that this is something that is complicated to do in general, no? Especially when we are talking about big systems where heat flows by many degrees of freedoms with many mechanisms like phonons, photons, electrons, or convection, many different ways of for heat to flow unavoidably between a hot reservoir or a hot part of the system and the cold one. So what we want to do is to explore smaller configurations with few degrees of freedom where we can learn how to play with this heat control. So this is something we've been doing in the last years with a lot of people. Now you can see them. So I won't talk about all of these works, but at least I wanted to put them here because we learn about all of these collaborations. One of them is here in the audience, Jose. We are doing we're continuing on work on this subject nowadays. So this is something I will talk at the end of the talk. And okay, so this is basically what I just said. If we have a big system with many degrees of freedom, and big in this sense means that the system is larger than the scale of thermalization of the particles that move in the system, then heat is difficult to control. But if we go to nanoscale systems where quantum transport usually take place, these systems are usually smaller than the scale of thermalization, so you can assume that particles go through the system without thermalizing and without losing much heat in the process. So this is also the regime where you have in all electronic devices where you have nanoscale transistors or devices that are in this regime. So it's also where we can control what is happening at this nanostructure that we can control with magnetic fields, with gate voltages, and many other ways. So this is where we are going to work, more or less. The transport in this kind of systems has been investigated in the last decades, but only for charge, or mainly for charge. But for heat, the experiments are much recent. So, for example, in 2013, 17, basically in the last 10 years is when labs have started to measure heat currents in these kind of setups. So, for example, you can measure heat currents down to the quantum of thermal conductance by measuring the temperature of this metallic plate and controlling how many channels you are able to inject heat into the system. Also, if you have an atomic contacts like this one that you can pull and control the number of atoms of the width of this contact, you can also control how much heat flows into the system. Or also single-electron transistors in metallic junctions like this one, where you have a metallic island where you have electrons that flow, that tunnel one by one from the different reservoirs. This is one reservoir, the other one. So there are tunneling barriers here and electrons that go through the system. And then you can measure the heat, the temperature of this system with these superconductor electrodes that measure the temperature very accurately. So you can measure, this is the same picture but in a schematic way. You can control how much heat you put into the system with these two fingers, and with these other two you can measure the actual temperature of the system, so you can infer how much heat has flown through the device. And also with photons you can control how much heat flows from one metallic island here that you can heat, and this heat propagates along this waveguide. And then you can measure it here, and again, this goes to the quantum limit. So the kind of, we are going to talk about theory, basically. So the kind of theory that works well for these kind of systems is, at least in a simple description for non-interacting electrons, can be seen in this way, where you can have two kinds of currents, the charge current and the heat current, flowing from terminal 1 to terminal 2 through a nanoscale junction or mesoscopic junction that is described by a scattering matrix S. So the square of this matrix is gives the transmission probability for electrons to go through the junction, and this is what determines the current. So the more transparent the junction is, the higher is the current, typically. No? So you have to compute the integral of this transmission with the difference of Fermi functions. For the charge and for the heat, you just have to include the energy with respect to the Fermi level in the integral. So a simple example of how this works is if this transmission is given by a resonant tunneling barrier that is described by a Lorentzian function like this one. So in this case, in the configuration that we are going to look at, when we have a hot terminal here and this one is cold, what you have typically is that in the hot terminal you have more electrons over the Fermi energy, so these electrons are allowed to go through the system to the right, and from below you have more electrons in the cold one than in the hot one. So electrons will tend to go in the opposite direction. So if this transmission is electron hole symmetric, you will have no current. But as soon as you move the resonance energy of this peak, then you will have more electrons. The transmission favors hot electrons, for example, going from right to left, and then you have a positive current, and when you put it below the Fermi energy, then you have a negative current, so you can modulate the sign of the current that you generate just by the temperature difference of the two reservoirs. If you look at the heat, both electrons have these electrons going positively carry a positive heat, and electrons going in the opposite direction have a negative contribution because they are below the chemical potential. So then this also gives a positive contribution to the heat current, and then the current is always positive. So this is something that I already mentioned, that heat cannot be controlled as well as the charge. You will always have heat going from hot to cold as the thermodynamic laws describe. So this is something that one learns in thermodynamics. Okay, so what we want to do is to try to control this heat. So one device that is expected to do that is a thermal diode. So what we want is that we have a system where if you have a high temperature here in terminal 1, you have a forward current flowing from left to right, and if you hit on the other side, you have a different current. In principle, it can be different. So if we find a system, a configuration where this current is high, but this one is small, then you have a rectifier, and then this gives a thermoelectric or a thermal diode. So if we look at how this behaves in this configuration, where we have conservation of charge and heat, at least at 0 voltage, so all the charges that enter from 1 go to 2 and the opposite. In these two configurations, if we look at these formulas, this is temperature independent, so the temperatures only enter in the Fermi function. So if you reverse the distribution of temperatures, you just have a minus sign both in the charge and in the heat currents. So this means that both the forward and backward currents will be exactly the same, and then there is no rectification at all. So this is bad for what we want to do, no? So it's a bad start for us. This is, well, we will discuss this later. This is basically because we have here transport is totally elastic, so electrons conserve energy when they go through the system. Nevertheless, there are a few experiments, not so many, but there are a few of them. I put here 3 that are representative. One of them in nanotubes. This is a bit older, but not so much, where they have a nanotube here, and then they can control the temperature at both ends of the wire. So they measure asymmetric and asymmetric wires, and they find rectification in this case, but not in this one. So this also is intuitive, because if you want heat to flow differently from left to right than the opposite, you need some kind of asymmetry between left and right systems. So here is the width of the wire. But here this is a complicated setup, because it depends on phonons and the dynamics inside the wire. So it's not totally controlled or known what is happening there, but at least the effect exists. There is a more recent one on tunnel junctions between a normal and a superconductor, like this one here. So this is the superconductor, this is the tunnel junction, and here is the normal metal that can be heated up. And here they measure a rectification due to the difference in the spectral functions of the superconductor and the normal metal. So the gap of the superconductor is playing the role there.
But is this possible in your setup, in your theoretical setup?
I will discuss this later. Yes. The answer is no. Yes. So we need something else. Okay. And then the other one is in qubits. So here this is a Cooper pair box where in a superconductor. So basically you have a qubit here with two Josephson junctions. I won't go in the details here, but this forms the qubit, and then with these resonators you can control the frequency of the photons that excite this qubit. And then at the ends here and here you have a resistor that can be heated up or cooled down, and then you can control the different temperatures between the two resistors, which act as the reservoir for photons. And then these photons propagate and excite the qubit, and you can also measure the heat current. Here the asymmetry can be seen, for example, in the different shapes of the resonator between left and right. So we have two common features for features. Well, you know. You need that the system is left-right asymmetric, and also nonlinear response. I didn't say much about this, but clearly if you are in the linear response regime where the heat currents can be written as a conductance times a temperature difference, if you reverse the temperature difference, you reverse the heat current and nothing happens there, no? And this is also something that we will challenge at some point in the talk. So this is the answer to your question. So what is happening here is that so if you have you only look at the heat current, you have is the same expression as before, the heat carried by each electron, the difference of Fermi functions, and then here you need the spectral function of the superconductor. But if you reverse the temperature in the Fermi functions, in principle you have nothing. You reverse you put a minus sign and nothing else, no? But here you have also phonons in the system. So the two you have phonons everywhere. The point is that the superconductor is weakly coupled to the phonons. but the normal metal has a stronger coupling to the phonon bath. So then you have a heat leakage into the phonons that is asymmetric now because of this difference of couplings. And then this is what introduces the rectification, which is indeed quite high. I didn't show the figure, but it can be quite high depending on the size of the gap. But now this is a 3-terminal problem, so it's not a 2-terminal diode. So the diode is expected to be a 2-terminal device. This is 3-terminal because the phonons are the 3rd terminal, or the environment in different cases. Now for the rectifier, what they measure is, again, the currents depending on whether they hit on one reservoir or on the other. They see different, well, basically the features you see that are more or less the same but inverted. But if you compare them and subtract some offset, you see that there is a rectification coefficient that is finite, quite small, but finite and reproducible. So it's something that is not just noise in the system, but it's something that you can modulate with the magnetic flux that you put into the qubit. So it's a real effect. The problem here is that this effect, these features are there is not a good model to describe them yet. So what is actually happening here is not clear, but at least the effect exists as well. So this disagrees with simple models based on the spin boson model. So here what we have is a harmonic oscillator with n levels that can be excited by coupling to the left and right reservoirs by absorbing photons either from one or the other. So if we have a harmonic oscillator with infinite number of levels all equally spaced, then the system is too harmonic to rectify. So the current that you get there, the heat current, is again totally symmetric with respect to the change of the temperatures in the distribution functions. Now this is the Bose function, but again, if you change the temperature of L and R, there is nothing here that gives a different modulation. But if you consider a qubit with only two states, so you have just the ground and the first excited state, then the current looks a bit different. You have here the difference of Bose functions, but now you have here the Bose function again in the denominator, here and here. So now if you change the temperature, the prefactor changes, and this introduces a finite response. In this denominator is basically the sum of rates for electrons to be absorbed and emitted from the qubit. So that's why you have 1 plus 2 times the distribution. Why one works and the other one doesn't is difficult to say. My interpretation is that if you have only 2 levels, you cannot have, well, if you have infinite levels, you can excite the system as many times as you want. So you absorb one photon, then another one from here, and then they can be emitted into the cold reservoir at any time. But if you have a qubit, once you absorb one photon, for example, from the hot reservoir, you cannot absorb a second one until the system relaxes and emits a photon to the cold reservoir. And this correlation between the two processes is what I interpret as giving this effect here. So what we need now, what we learn from here is that we need something else, which is that the system dynamics play a role in the system. For instance, with some correlations or with some if the state of the system given by the scattering by the density matrix of the system depends on the two temperatures. Yes.
Can you see this coupling to the spin boson to this reservoir not just as a third lead as well?
Well, no, because here the coupling is the coupling to its bosonic reservoir is doubled here, so you have 2 couplings there. Yeah. You could have a third one, but then it's a different problem. Yes.
Somewhat related question. So already in this language, once you have the rate, can you understand everything in terms of a kind of classical master equation without any quantum configuration?
Yes. For this, it's very simple. Yeah.
You don't really need a qubit, no? Any 2
No, just 2 levels. Yes. Yeah. Yeah, I will show a bit with a bit more detail for the quantum dot. There is an analog for this system a bit later, but yeah, there is no coherence here at all. Yeah. So there are theory proposals for different thermal diodes in basically following this proposal with qubits in superconductors. You can have also more complicated setups with 2 qubits that are coupled inductively to each other. Or you can also have a Q-treat with 3 states instead of 2, and here the asymmetry is clear because you can couple the hot reservoir to 2 transitions while the cold one is only coupled to 1, for example, and here you can control the asymmetry of the setup. But okay, this is another story. So this is the outline of my talk after, well, not so much. It could be worse. So this is basically the 3 problems I mentioned so far. So and I will now go in more details afterwards. So one is what happens when we have correlations. For the electronic case, this means when we have strong interactions and weak coupling between the system and the 2 reservoirs. And now this will be classical, well, not always master equations. Then what happens when you couple to the environment and you have not 2 but 3 terminal setups? And then what is missing in the conductor, in the elastic conductor that I presented first, where we had no rectification. So what we are missing is thermalization in some sense in the center of the region, and this is what we will discuss, and this is what is still work going on. Okay, so for the correlations. This is the analog of the qubit that I promised. So you have a quantum dot where you can have electrons tunneling through these 2 barriers from the 2 reservoirs into the quantum dot. If the interactions, the Coulomb interactions are very strong, you allow only 1 electron in the system. So the states of the system is just 0 or 1. And then you can write the master equation for the setup. This is the Lindblad equation, but it's just a rate equation that considers all these tunneling rates for electrons going in or out. So for electrons going in, you have the tunneling rate with a Fermi function, and for electrons tunneling out is the same but with 1 minus the Fermi function. So with this you write the heat current and the rectification coefficient as the difference of the forward and backward currents, normalized by the sum of the 2. So this is the best way we found to quantify this effect. So now in the case where you have spinless electrons, so the 2 states of the system are just 0 or 1 as in the qubit, then the heat current that you find is again the bad one, in the sense that there is only the Fermi distribution function multiplying a temperature independent prefactor, and this gives no rectification. So contrary to what happens with the qubit. So we need to complicate things a little bit more, not too much. So you consider, for example, that you have a spin. So the electron has a spin, which is actually the case, no? So then you have 2 levels that the electron can occupy, depending on if it has spin 1 or down, up or down. And then what you recover, if you do so, is this heat current that again has the distribution functions in the denominator here. Now we can interpret this a little bit better, because now this, in comparison with the spinless one that has no distribution function here we have an asymmetry between processes going in and processes going out. Because if the system is empty, there are 4 possible transitions for electrons occupying either of the 2 levels. But once the quantum dot is occupied, there is only 2 transitions, because you know the state of the system. So it can only go out from this particular state that the electron is occupying. And this asymmetry is what reflects in this configuration here. So, well, this is how the currents and the rectification coefficient look like as a function of the position of the level and the separation of the 2 levels. I also don't want to go much into detail. Just look at the rectification that you observe here, between the difference between the forward and backward currents. there is some rectification, but very small, no? So the rectification coefficient is something like 0.02. It is better if you increase the separation of the levels, but not so good, no? So we can do better. Actually, by going from 1 to 2 states, we learn something, that is that the number of states that you can occupy have an effect here, even if the two states are have the same energy. So, for example, if you consider not one quantum dot but two that are coupled such that you again only allow one electron in the two of them, then you can increase the current, the rectification coefficient that you obtain. And the larger the number of these available quantum dots that you have, the higher the rectification. So, for example, if you have 100 quantum dots, you have 1/2 of the rectification coefficient, which is pretty good, no? You want to go to 1, and you do this with an infinite number of quantum dots, but of course you cannot have an infinite number of quantum dots with only one electron, no? With 2 you can do, with 3, yes, but as you go to 5, also doesn't work. But okay. So now if you restrict to the case of having 2, again with 1 quantum dot, and now there is a coherent tunneling coupling between the two of them, so the electron becomes delocalized between the two quantum dots. You have this Hamiltonian of the system with the energy of the left and right quantum dots and the tunnel coupling. So if you diagonalize the Hamiltonian, you get the superposition of the left and right electrons that hybridize like in the hydrogen molecule, for example, with the bonding and anti-bonding state. So this is what you get here. You get different wave functions for this state and for this one, and they also split. So even if the two electrons, the separation between the two states is now given by this square root. So which is always finite due to the tunneling coupling, no? Then also, as this wave function has a different distribution depending on the position of the level, it can couple more to one lead than to the other. So this is reflected by the tunneling rays that you put here. So this allows to control the asymmetry of the reservoir, of the coupling to the reservoirs, because you can make this alpha minus big, so this is coupled to this one but weakly coupled to this one, and for the other one you get the opposite. This is coupled here but weakly coupled there, and this you can control with the position of the levels. So again, with this you improve how the rectification behaves, so you get a larger rectification here. The coefficient can be much larger, now 0.2, something like that, when the two levels are well below the Fermi energy. But also in a region where the currents are very small. So here the difference is large, but also the currents are small, so it doesn't work very well. Yes?
I had lost, I'm sorry. So if you have 2 now, and you could have 3 and 4 and 5 and 6, then in the end you would have, in a way, a setup again where you have one terminal here, one terminal there, and you have simple conductor. And there, you should not have any rectification effect. I mean, this is the example you said before. I mean,
if you have a large one and then you allow for a lot of electrons, or if you well, as long as you allow for only one electron, then in principle you can have. Now, I will show an example with.
It's highly nonlinear.
Yeah, and also because the state of the system, as before, the state of the system depends here. The state of the system depends on the temperature of the reservoir. So the occupation of this dot depends on temperature in here and here. So everything, the state of this system is composed of the two temperatures, and then if the system is asymmetric enough, this combination can give rectification.
So
The larger the system, maybe the worse, but
you say that if one lead would be interacting with the other leads, you would also have it in a normal setup.
If you have current from one lead to the other directly.
I mean, in a way, you told me that the two leads are kind of talking to each other. Normally, the setup in Keldish is that there's only a coupling from one lead to the
yes.
system, and then another coupling.
Yeah, this is what we have here also. So you only have tunneling from the reservoirs to the structure in the middle. So from here to here, then here you have the electron spends here some time before it goes to either of the two reservoirs, and then it goes to the second one, but not direct. There is no direct coupling like in resonant tunneling. So this is a different. Here the system is the state of the system is a thermal state that depends on the two reservoirs, out of equilibrium but thermal in some sense.
Yeah, I got lost, but we talk
Okay. Okay, I hope at the end I will have you back. Let's see. So so here you can control the symmetry of the wave functions. If you have a triple quantum dot, you can do this in a better way. So for example, if these two are coupled to one reservoir and this one only to this one, then when you diagonalize the system, you have three different combinations. But in particular, you have this one when the energy of these two are the same. You have this superposition between the state of A and B. That does not include the third quantum dot. So when you occupy this superposition, namely this one, the electron cannot go to the right. So electrons that occupy this state can only go back or just stay there. No? So this has a big effect, because if this state is below the Fermi energy here and this is cold, then at some point this state will be occupied, and then it freezes there and the dynamics are blocked and there is no current flowing there. So, and this is what happens here in this regime for the full lines when you tune the energy of these two levels. So as soon as they go below the Fermi energy, you have this effect. But if this one is hot, you have the electron can go out to the lead, because there are empty states there to occupy, and then you can have the occupation of this state doesn't block the current. So then you have a higher current here, and this is a big effect because you have a peak for the forward current, and a total suppression for the backward one, and this is now. This achieves rectification coefficients of order 1.
Is this defacing the position of the dark state loses the phase?
Yeah, if you allow for defacing here, then this will make the occupation of this state leak into the other ones, and then you lose the effect.
It's not what you.
No, I didn't consider it here.
Fluctuations for its charge noise, for instance.
Yeah. Yeah, as soon as you lose this superposition, then the electron will be allowed to go to the right at some point. So now this is a coherent effect, differently than before. Yes?
You don't do the same with a system that has a gap. You put in the middle region like a superconductor, and you discard some part of the transport.
If you manage to couple to one part of the system but not to the other one, maybe yes. Well, we do something maybe similar in the next slide. So if this doesn't answer your question, we can go back to that. So now the second part is when we couple to the environment. So when we have not only two terminals but a third one, how much is, well, okay. So now we lose some heat into the environment in the center of in the junction. Well, not next slide, but the following one. So basically, we can understand here this in a simple way. Now we have this heat dissipated into the environment that avoids the conservation of heat in the system. So now current in L and R are not necessarily the same. And even if you go to the linear regime where you write the currents in terms of conductance between terminals L prime and L, times the temperature difference between the two of them. For example, for the forward current here, you have current going from 1 to 2 and from 1 to 3 contributing to the current here, and for the other one you have the same but from 2. So as soon as this current and this one from 1 to 3 and from 2 to 3 are not the same, for example, if you have here a strong barrier and here a thinner one, so these electrons, once they pass this barrier, they can easily go to the right. But if those electrons going from here, they go into this barrier and then get into contact with the environment, then they lose heat here, and then once they pass the system, they have less heat, so then these two currents are clearly not the same. And then even in the linear regime, you can have a current. So now you can play with gaps here. So this is what we consider following the tunnel junction experiment that we discussed before. If you have a metallic island here and then two superconductors with forming a ring here, and then here with a normal metal, so this is a weak link. And here in this link, the flux of the superconductor can control the size of the gap. So basically, the different size of these two loops means that the flux in the two of them will be different. So applying a magnetic flux, you can make this gap larger than this one or the opposite. So then if this one is larger, for example, heat will easily go from this side to this one. But from when the small gap reservoir is hot, then electrons that tunnel from above the gap here cannot go to the left because of the gap, because here there are no states, so they cannot go there. So then they stay in the metallic island, then they relax energy and they can go back to the right. So then again the two processes are asymmetric. And then, no surprise now, I hope, you get a finite rectification coefficient that now you can modulate with the flux that you apply here. So interestingly here with this flux, you can make larger the gap of the left or the right one, depending on the flux. So you can make the rectification work in one direction or in the opposite, so you have a bipolar diode here. A simpler case for this effect is if you consider the quantum Hall effect. Sorry, there are too many configurations and very, very different, but here what you have is a 3-terminal setup with edge states, so electrons can only flow through the edges along these arrows here. So if your system is now the two lower terminals, then when this one is hot, electrons flow without any problem to the right one, so the heat current is the thermal conductance times the temperature difference, and this is finite and well controlled. But when you have the opposite situation, electrons flow along this line, and then all the heat is lost here and put into the third terminal, which is playing the role of the environment. So then at this terminal there is no heat flowing at all. So here you have a perfect effect that in one polarity you have the largest current that you allow for, and in the opposite you have zero current. So this is in principle a perfect rectification. It works in the linear regime, but now this is clearly not a diode, no? Or at least this is the most extreme case of a 3-terminal setup, because the third terminal is playing a very strong role here, no? And here the asymmetry is played by the magnetic field, by the way. So okay, this is not we cannot call this a diode, but at least it makes the job if you are only interested on the lower terminals. There are more examples, but I think I will skip them because there is no much time.
Sorry.
Yes?
In the other, you say that without a magnetic field, it would not work. I mean, if you just assume that you have some edge states.
You mean with a topological insulator or so on? Yeah, then you have two channels. I think it won't work, or maybe yes. Yeah, maybe yes, because you will have, as soon as in the topology insulator, you have electrons going in different directions in the two channels. So then you will always have one electrons going this way and this way, so you will always have current from here to here. Okay. So you would need something else there. Yeah. Okay, yeah, so, well, you can, this is just to say that you can control the coupling to the environment if you put it in a two-terminal conductor and you hit, well, and this is an STM tip, for example, that you can move along the system, and then you can again find the rectification coefficients of order 1. But okay, I'm not doing very well with time, so I will skip this. So now the third part of the system, which is the one that is now in progress, is the thermalization. What's the role of thermalization? So basically we are comparing the elastic conductance that I mentioned in the beginning that gives no rectification with some kind of state more closer to the quantum master equations that I discussed with the quantum dots, where you have electrons that go from one terminal to the system, then stay there, something happens to them, and then eventually they go to the right. But they don't go directly from one to the other. So maybe this was your question before. So yeah, in the first case, if you have, well, this I mentioned before. In this case, you have the scattering matrix that gives the transmission coefficient for electrons going through the region. So what happens if we allow for some thermalization on one side of the conductor? So electrons that go from here to here, in this region there is some inelastic processes or something where electrons lose their phase coherence and thermalize in some way. So the way to do this in scattering theory is to introduce a probe terminal. So again, a third terminal where electrons can go into. So this is a different scattering matrix. So this is the same as this one, but here you have a scattering matrix for electrons going into this terminal from both sides. But here we want to impose that this terminal is not injecting neither particles, neither heat. So this is different from the three-terminal device. So this is a third terminal, but it doesn't break the conservation of charge or heat. And for this, what you do is that the chemical potential and the temperature of these probe terminals are floating. So it's like a thermometer. So they evolve until this condition is fulfilled. So this is what a thermometer does. So for example, to see it in the simplest case where this scattering matrix is transparent, so every electron from 2 goes into the probe and then goes back to the system. And also from the left, so there is no scattering there. Then you can write the charge current as the transmission coefficient for electrons going from 1 to p. So how much probable is for electrons to go through this one, and then they are absorbed here. And then, well, this is in the probe, and then this is the contribution for terminal 1, and from terminal 2, which is in this case, in the forward case, this is the cold one. Then there is no transmission here, so you just have the difference of the Fermi functions. For heat, you have the same with E here. And now if you look at the current, the forward current here in terminal 1, there is only the contribution between the coupling between 1 and P, so you only have this term that is the same that you have here. So you can calculate directly this integral because it's minus this one that you know you can calculate it is the difference of the chemical potentials. So with this you get the difference of the chemical potential in the probe and in terminal 1. And for the heat you have now the difference of the square of the temperatures of terminal 1 and the probe terminal.
By this you change the definition of the scattering matrix, because scattering matrix is really including all the leads in the equal. Now you change something.
if you have here a finite scattering matrix, then you have to compose the two of them and have a total scattering matrix of the system, and then you compute this with the as you said. But and then you won't. No, you will if you have a look for these things. Yes.
If you don't have any
I will.
or a thin flow, you won't have it, I guess.
You will. I will show it later. But if there is no scattering matrix here, then all the transmission coefficient is purely by this one, so there is nothing else to consider. And then there is the current flowing from here to here. This is just the Kirchhoff law, the current from here to here and from here to here, and the different contributions of the current. But you can separate, split the different parts of the current. So you can do the same for the backward currents. It's basically the same, but now you have different temperatures and different. So the probe, the chemical potential of the probe and the temperature will now be different. So now the ratio of the two currents is now the ratio of the chemical potential difference between the probe and the system and the different temperatures. So as soon as this is finite, you will have a thermal diode, a thermoelectric diode for charge, or a thermal diode for heat. So as an example, for example, you can have this case with two quantum dots. I chose this because you have a larger effect, so you can have two dots with two resonances at different energies here. And then as you control, here you can control the position of the resonance in 1 and 2. So this is, for example, for 1, and then you get different currents for the forward and backward currents. And the thermoelectric rectification go up to 1. The thermal rectification is a bit smaller, but you still have something like 0.2, something like that. But you have a finite effect. And this is just because you lose the coherence of the electrons there. And then this is what makes it asymmetric for electrons going from, if the energy of this dot and this dot are different, so you have a splitting like in any point here, for example, then electrons, the temperature, the effective temperature of the probe here will be different depending on whether this is hot or this is hot, because if the energy of this, for example, consider that the energy of this dot is very high over the Fermi energy, then there will be no electrons going from here to here. So if this is hot, then there is no transport here, and the temperature of this region will be colder. While if this is hotter now, and this one is allowing for electrons to go into the middle region, the temperature here will be hotter, and then this difference of the temperature, depending on which side you heat up, is what gives the effect at the end. Okay, well, okay. So this is what gives the effect. So even if you have no leakage there, just by losing the coherence and allowing for some thermalization, then you get the effect. So you can have other effects if you allow if you go to the nonlinear regime, even in scattering theory. So in the equations that I mentioned before, the transmission is totally independent of temperature and voltage and everything, but this is not necessarily the case if you go out of the linear regime, because for example, consider that you have a tunnel barrier like this one. These are all electrons, and then you apply a finite voltage here. This is the simplest case to consider. Then the whole potential of the system is affected, not only the chemical potential of the reservoirs, but also the barrier is affected by this. So if you take into account this with some injectivity, some machinery that I also don't want to go into the details there, then you can take this into account and obtain what is the potential of the system in every point of space. So now this affects the transmission coefficient. So now this potential changes whether you hit on one side or on the other. So this will be different in both cases. So you can also consider this, and then you see that the effect is modulated with respect to what we saw before. Well, here, for example, it changes sign. So here you have a positive rectification, and here you have negative, but now you recover the positive one here, so there is a strange effect there. And also for heat, you have a larger response now in this case. This is in the case where you have both effects, thermalization and screening or charging effects. So that's all, finally. So this is what I talk about. So in the three parts, so the three main problems that we faced along this year. So one is what happens when you have correlations, and this is what you need, at least in the weak coupling regime. So in electronic systems, you allow this with Coulomb interactions. And then there are different effects that you can exploit, even the degeneracy of the system by increasing the number of allowed states, or even quantum interference effects can play a big role here. What we have to note here, especially with respect to the rest of the discussion, is that in this density matrix formalism, the thermalization of the electrons in the system is implicit. So the state of the system is thermal at all times. So then you have the rectification due to coupling to the environment. So this is also something that you can avoid in the experiments. I once talked to the experimentalist of the tunnel junction that I mentioned before, and then I told him, no, but this is not a thermal diode. No, you have heat leaking into the phonons. And then he said, yeah, but you have to live with it because it always happens in the system. No? So in some sense, you can reconcile yourself with these systems being a good diode for heat, because you cannot avoid it. So what can you do? So the good thing is that you can have this rectification also in the linear regime, and that you can couple how this works with different couplings in the different configurations that I discussed. Current is not conserved, but okay, this could not be a problem. And then the last part is the effect of thermalization and how to include it in ballistic systems or in more quantum coherent systems. And so we are now working on this. We are exploring how this goes with nonlinear effects, and how much you can, what is the minimal configuration where you can have a rectifier in a quantum conductor. So with this I finish, and thank you for your attention.